Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Lee Harrison of Siemens EDA. We're going to talk today about moving security into test. So, Lee, when you think about security and test, they typically don't go together in the past. What's changed?
So what we've seen in the last year is really a massive uptick in the focus of security with electronic products in general, right the way through from the end product, right the way down to the IC. As you mentioned, security doesn't necessarily fit with the test domain, and I think in the past we've seen a lot of that. But really the key learnings for everybody this year is that security really needs to be part of the design. And given the number of requirements that we're seeing coming through for kind of in-life data collection, in-life testing, in-system testing, the need to be able to get access to the test structures in life has become really, really important. So what you've seen in the past is access to our typical test structures such as test compress and SSN have typically been only available when the silicon's been in a safe environment on premise, and those features and access mechanisms have been disabled before the silicon leaves the fab. But now with all this in-life requirement, we're seeing need to kind of keep those access mechanisms open so that we continue to be able to test and monitor the silicon throughout its whole life cycle.
What's the driver here? I mean, we think about automotive, that's one of the key drivers because everybody's worried about designing these systems so they don't turn off the road with somebody else controlling the car. Second one would be more mission critical, more valuable data.
Yeah, no, exactly. So this is kind of one of the areas where the worlds of safety and security kind of cross over. So on one point, the automotive OEMs want to start collecting a lot of data around reliability. They want to make sure their silicon is working well throughout the life cycle of the vehicle. They also want to know up front when that silicon is about to fail, so they don't get any kind of immediate failures. They can do preventative maintenance. And on the flip side of that, with security, with vehicles and all of these types of products these days, there is a whole ton of bad actors out there trying to hack and get into the devices. So at the same time as being able to do predictive reliability analysis, we need to be able to detect any unwanted cyber attacks while these vehicles are out in the field. And the same goes for things like data centers and other applications.
One of the source of some of the breaches has been the fact that there's too much complexity. Another piece of that is that things break down over time. Circuits age over time. And as a result of that, you potentially have openings that you didn't have before too, right?
Yeah, no, absolutely. And that's all part of the continuous reliability monitoring of the silicon throughout its life cycle. The silicon's not going to last forever, and as we go down to the really kind of leading edge nodes, we don't know today what the reliability of those processes are going to be throughout the lifetime of that silicon. So we need to be able to do that reliability monitoring on the fly.
One of the issues you're talking about here is that reliability and security have now met, because in the past they were pretty much separate disciplines, right?
Yeah, and I guess one thing that becomes blatantly obvious when you work in both these domains is that even though there's the crossover there, what you find is safety is a very static landscape. So the requirements for safety don't change massively over time and the life cycle of the product. However, security is a completely different beast. It's very dynamic, and we don't know what the style of the attacks are going to be from one day to the other. And you see this in the way that we're putting the technology together. So safety is very well defined, very static, whereas the embedded analytics monitors that we're developing to monitor for cybersecurity attacks are extremely configurable. So throughout the life cycle of the silicon, you can continuously update the profile of those monitors to hopefully be able to address new threats as they come along throughout the life cycle of the product.
So this moves test into basically 4 dimensions, right? Because you're dealing with the XYZ axis of everything that's going on here, potentially in a heterogeneous package, but you're also doing this over time.
Yeah. Yeah, no, absolutely. And you've got to have the ability to be able to collect the right data as the vehicle or the product is out there in the field, and not only collect the data, but you've got to be able to analyze that data and determine what those cybersecurity threats are, to then be able to make updates to the monitors going forward. So there's a bit of a closed loop solution there in terms of making sure you can collect the right data, making sure you can analyze the data, and then fine-tuning your system going forwards.
In the past, when we looked at the advanced nodes, typically they were running in a fairly secure environment. You think about probably a data center, maybe your cell phone, where it's not really critical data for the most part. Now what's happening is these devices have to last a lot longer, but they're also being designed with the leading edge chips. How does that all go together, and what are you looking for from a test standpoint?
Several things from the test standpoint. From a manufacturing test perspective, there's this increasing need to have more and more advanced fault models. We've certainly seen a lot of discussion this year about silent data corruption. We're working extremely hard on trying to understand what new fault models can be introduced to try and detect those types of defects. And that's at a manufacturing level. Once you get into in life and in system, the quality of the tests that you're running, we're seeing the requirements there are also massively increasing. So again, you'll see some new products coming from us in the new year, which will be able to address those requirements and those new challenges.
In the past, also, when we dealt with chips, a lot of this was a single chip and it would be developed by a vendor for a socket or whatever it happened to be. Nowadays, what's happening is we're starting to get a lot more heterogeneous components in there, not all from the same source. They may not mesh together to the same as everybody hoped they would. In addition, they come from multiple different vendors. So how does all that fit together, and what do you do from a test standpoint? What's changed there?
Hopefully, you're all aware that earlier this year, we launched a multi-die test product. This enables the ability to run and test between the various die within those complex SoCs. And then you've got our SSN high bandwidth test solution, which is also very well positioned to be able to test across multiple chiplets and multiple die. So there's a lot of new technology that's kind of being introduced and being put together to try and address that problem.
One of the key technologies that's come along here is analytics that actually get into the chip. They're built in from the design side. How do you interface with those analytics? What do you do with this, and how do you send the alerts as you find something that is an aberration or an anomaly?
So our embedded analytics technology is really starting to grow in terms of its use cases and adoption within the security domain. We're seeing our on-chip monitors being used for a whole range of different applications in security. Everything from monitoring buses for illegal packet detection. We can generate signatures for secure boot to make sure that your device is completing the boot sequence as expected. We can do dynamic security token generation and even forensic data collection if you're unfortunate enough to have a security attack. And all of these monitors are being added into your design at an RTL level, and they're able to collect a wealth of data of what's going on within your chip. Now, some of these monitors, which we call our sentry devices, they're actually able to be reactive. So if they see something that is illegal or not expected, they can actually block transactions and activity there and then. We have the more passive monitors that enable data collection and data to be analyzed by an on-chip CPU running some analytics software. But I think one of the strongest points of this technology is the ability to be able to collect that data and take it off chip to a cloud-based system to be able to do more advanced diagnostics over a fleet of devices or a fleet of vehicles to be able to really understand what's going on out there.
Really, just having that data, understanding that there is a problem is not good enough, right? You really have to be able to do something about it, almost the way memory corrects itself with ECC memory.
Exactly. And I think this is one of the areas that we're going to see really develop over the next couple of years, because at the moment we're starting to add these monitors into designs. Customers are really excited about the data that we can collect, but it's still not fully defined how to use that data and where it becomes really important. So once you start to be able to collect that data, we're starting to see the emergence of AI type technology being able to analyze that data and really extract the important information out of that. And having done that, we can then feed back to the system to either enhance the operation, or in the world of security, we can tighten the security and really kind of introduce new checks for new potential attacks that we see coming along. And that's actually a really important part of being able to meet some of the new standards that are coming up. So if you take a look at the ISO 21434 standard, there's a part of that standard that really takes into account the fact that the dynamic nature of security in general. So it expects that over time there'll be new attack vectors that come along and allows for the ability to update and enhance the detection mechanisms over the life cycle of the product.
So putting this in perspective, what's really changed here is that the industry always talked about security, but really what's happening now is you're actually designing it in and you're following that security all the way through its life cycle, right?
Yeah, no, absolutely. And I think in the past, security was always added as an afterthought, and it was kind of the padlock on the outside of the chip. But now it's really designed in at every single level to make sure that every part of the design is protected, especially now that we're having to keep the test mechanisms and the test structures open to be able to do all of this in-life data collection.
One last question. So what does this mean actually for automotive? They're the ones that are really concerned about this right at the moment, because they're basically digitalizing the entire vehicle.
So from an automotive perspective, what's really been happening over the last couple of years is we've seen a lot of introduction of new standards and regulations. We've got the ISO 21434 standard that got introduced, I think, August 2021. And then from a European perspective and other countries, there's the UN ECE regulations. UN ECE regulations really define how devices handle the risk management of security. And then the UN ECE 156 really looks at, most importantly, over-the-air updates. So everybody's familiar with over-the-air updates. A lot of all the new cars are now capable of doing that. This new UN ECE regulation really defines the security measures that have to be in place for automotive OEMs to be able to do that. And if they don't adhere to those regulations, then they're not allowed to do over-the-air updates. So there's a significant amount of nervousness about making sure that they can achieve the requirements around that.
Lee Harrison, thanks for a great explanation.
Okay, thanks, Ed.